We will now look at sampling distribution of mean. We know when we've discussed properties of estimators, unbiasedness is an important property that we've discussed. We know that sampling distribution of mean has mean as an estimator of population mean is an unbiased estimator. Meaning what? Meaning, say suppose there is a population which is mean mu and variance sigma square, and we draw a sample from this population and we compute x bar on that sample. I call it x bar 1. I return the sample to the population, get another sample, I get x bar 2. I keep on doing this, I get say k number of x bars. If I compute the mean of all these means, if I compute the mean of these means, that is expectation of x bar is, I know it's going to be summation of I is equal to whatever it is, 1 upon n mu, which means it will be n into 1 upon n mu, which means it's mu, right? The sample statistics x bar is an unbiased estimator of its population parameter mu. That is, the average of all sample means would be the mean of the population. Now, the variance of this would be sigma square upon n. The variance would be sigma square. Variance of x bar would be sigma square upon n, and standard deviation, as we have seen, SD of the x bar is equal to sigma upon square root of n. Right? These are the things that we talk about. So basically, we also know that, which means that if I have a distribution of x bar, sigma upon square root of n is a standard deviation of that distribution. So sigma often is not known, and I replace sigma by s, and I also know that this is a standard error of mean. This is a standard error of mean, and I can use the standard error to make some kind of a judgment about about the population parameter. Now, what I am trying to do in this is I am trying to take a population of only 3 observations. This population has only 3 observations. One value in this, so I have a population. I know there won't be any population which has only 3 data points, but suppose I have a population that has 3 data points. The first data point is 3, the second data point is 5, and third is 7. Now if I add them up, the total is 15 divided by 3 data points that I have is equal to 5, right? So the population's mean is 5. I have a population, I know in reality I will never have a population of 3 observations. Okay, now let's do some interesting stuff with this and understand what actually happens. Okay, what I'm trying to do is I shall take my n is equal to 2. Now I'll keep my n is equal to 2. My sample, my population size is 3, so I'm keeping my n is equal to 2. Okay, so I'm taking a sample of a size 2 from my big population of size 3, right? So, I take first sample. See, I call these sample 1, sample 2, and so on and so forth. Okay, so I call it sample 1 and so on, 2, 3, 4. Okay. These are my samples. Okay, I have first value from the sample. I'm taking n is equal to 2, right? So first say participants 1 value and participants 2's value, right? I have these two values, and then what I'll do is I'll compute the mean. I'll compute the mean for each of the sample. Okay, so I take a random sample from the population. For each of the sample, I will have a mean computed, right? Say for example, my first sample is 3, 3. Okay, first I have n of 2, so I take first randomly I take two values. So one value is 3, another value is 3. The mean of the this particular sample that I have got is 3 plus 3 upon 2 is 3. That is 6 upon 2 is 3. Now suppose I go for the second sample. The second sample is 3 and 5. Okay, 3 plus 5, 8 upon 2. The mean is 4, right? Mean is 4. Okay, I take third sample. It is 3 and 7. Okay, 3 and 7, 10 upon 2. 5 is the mean of this sample. So these are my sample means. Okay, now suppose my first is 5 and then I get 3. So fourth sample is, first participant is 5, second participant is 3. It's again 8, the mean is 4, right? Then I get fifth sample 5 and 5, right? It has a mean 5, needless to say. I take a sixth sample 5 and 7, right? So first participant has a value 5, second participant has a value 7. This is what I mean 6. Okay, I take a seventh sample from this population. First participant gets a value of 7, second participant gets a value of 3. This particular sample has a mean of 5. 7 plus 3, 10 upon 2, 5. The eighth sample that I am taking has first participant having a value 7, second participant having a value 5. It's totaling to 12, has a mean of 6. Right? My ninth sample has first participant has a value 7, second participant has a value 7. 7 plus 7 upon 2 is 7. Right? Now, once I have this kind of a data, what I have basically done is if I'm drawing two samples, a sample of a size 2, sample of a size 2 from a population of a size 3, then these are the all possible samples I can draw. Right? These are the all possible samples I draw. These are all possible sample means for this particular sample of this particular size for a population of this particular size. Right? Now, what I can do is I can do the sum of these values and find what is the mean of the means. Right? If my theorem says that sample mean is an unbiased estimator of a population mean. So, population mean is 5. This is mu. This is mu. Okay? These are my sample means. So, there are times when sample mean is 3, there are times when it is 4, there are times when it is 5, there are times when it is 6, and there are times when it was 7. So, with this kind of population, I get sample means from 3 to 7. Right? You also realize that the probability of getting each is not identical, but that's not the question that I'm right now concerned about. Okay? So if I add them up, what's the total?
45.
45, are you sure?
Yes.
Yeah. 45 divided by how many samples we have?
9.
9 is equal to 5. So means of all samples is equal to the mean of population. Okay? My sample mean is an unbiased estimator of a population unit. That is, mean of all means is population. So this is actually expectation of x bar is equal to 5 is equal to mu. Right?